We are already with 55 people now. I just checked, it's all over Europe. Quite nice, quite exciting, I think, to have all these people together on this, yay, on this webinar. So let's continue. The first speaker will be talk about the policy perspective on connectivity in European rivers. Jean Bugaba, can I ask you to start? Jean?
Yes.
Yeah.
Yes, good morning, everybody. So I will show my presentation on the screen first. I hope it, okay. Slideshow, okay. Okay, can you hear me? Okay, very good. So good morning, everybody. My name is Jeanne Bougaba. I'm working in the Commission in DG Environment. And before starting, I also wanted to thank the AMBER team and the World Fish Migration Foundation for organizing this webinar. I think it's really amazing that due to the circumstance, we can still organize these workshops. So I'm very glad. So I will present you, to start with, an overview of the different EU policy that aim at restoring connectivity in European rivers. So first of all, why should we restore river continuity? I'm sure you're all convinced, but just in case. First of all, to start with, aquatic ecosystem are not in good condition overall. This is shown by the latest report from the IPBES on the global ecosystem assessment, which shows in particular that inland water and freshwater ecosystem show amongst the highest rate of decline. And also it shows that freshwater species population have suffered from 81% decline. So this is a major issue worldwide, and in particular in Europe. And one of the cause of this decline is due to multiple pressure, but those pressure include in particular river fragmentation that causes modification of flow, also acts as barrier to migration and to sediment transports, and also destroys habitats. So it has impacts also on ecosystem services that are provided by freshwater ecosystem. And in particular, amongst those ecosystem services, I would mention water supply, flood protection, food supply, recreational activities, and protection of coastal zones. So in terms of the policy context, to address those problems, we have different policies that have been put in place at EU level. Those policies aim in particular at halting and reversing the loss of biodiversity in European rivers and to reconnect ecosystem. So amongst those policies, I would mention in particular the Habitats Directive, the Water Framework Directive, the eel regulation that aims at particularly protecting eel, a specific species, biodiversity strategy, also the strategy on green infrastructure, and in terms of new projects, the environmental impact assessment and the strategic environmental assessment directives. I will present those policies a bit more in detail later. Also, I wanted to mention as a recent development the publication of the communication of the Commission on the Green Deal, which is very important because it puts environment on top of the priorities of the new Commission. And in particular, in relation with biodiversity, there are two main announcements in this communication. First of all, a biodiversity strategy will be adopted, and it will set objectives for 2030 to protect and restore biodiversity. And also, the EU will work for an ambitious new global framework to protect biodiversity worldwide at the UN Biodiversity Conference in October 2020. Maybe to explain a bit more about this biodiversity strategy. This strategy will contribute to achieve the targets of already existing legislation, such as the Birds and Habitat Directive, the Water Framework Directive, and the Marine Strategy Framework Directive, but it will set some ambitious targets in order to reach these objectives. And it will also seek to bring a resilient nature back into the wider landscape and into urban area. And as part of this strategy, we are now looking to improve connectivity of ecosystem, and that includes river connectivity through, in particular, measures such as removal of barriers and restoration of floodplains. So this strategy should hopefully be published at the end of this month. So now I will go a bit more in detail into presenting the EU policies related to river continuity, and in particular, first by presenting the different objectives of those policies. It's important to emphasize the fact that EU policies, the different EU policies, set complementary objectives to reach common, to reach overall the same goal. Of course, I would start by presenting the objective of the Water Framework Directive, which is an overarching objective, which is to reach in all rivers, lakes, transitional and coastal waters, good ecological status by 2027, the latest. And of course, another very important objective, which applies also to all water in the EU, which is the non-deterioration, the obligation of non-deterioration of status of water. So achieving this objective is closely linked to continuity, of course, because it requires to put in place measures to restore connectivity of ecosystem. And it's also important to emphasize the fact that river continuity is explicitly mentioned in the Water Framework Directive as one of the quality elements. I will not go too much into detail on this aspect because I know that my colleague Martina Bussettini will make a more detailed presentation about the link between the Water Framework Directive and continuity. So in addition to this objective, we have the Habitats Directive that sets objective to protect habitats in Natura 2000 sites, and in particular to maintain and restore those habitats in favorable status. And also there is an objective which is to improve ecological coherence of the Natura 2000 network. I also wanted to mention the eel regulation. So the eel regulation is targeted at one specific species, which is the European eel, and it aims at protecting and restoring eel population. And also, in particular, one of the targets is to reduce mortality of eels due to different causes, and to achieve 40% of natural escapement to the sea of eels. And to finish, the biodiversity strategy, which sets objective for 2020, which is that ecosystem and their services are maintained and enhanced by establishing, in particular, green infrastructure and by restoring at least 15% of degraded ecosystem. So now I will present the different instruments that exist, in particular to achieve these objectives. So in terms, first, I will start by the planning instruments, which are very important, and in particular, River Basin Management Plan, which is a planning instrument that sets measures and management objective for an integrated protection and restoration of aquatic ecosystem in the EU. We also have, in terms of planning tools, the national eel management plans, which set measures to reduce eel mortality and enhance their habitats and river continuity. And we have also the Natura 2000 network, which sets some, in each site, some specific management planning and objectives to restore habitats. Then I wanted also to mention the financial instruments that are also, well, European financial instruments that are also very important because they can be used to finance measures to reach these objectives. So I would mention the LIFE instruments and the European Structural and Investment Funds. Also, some specific type of measures that are now more and more promoted also at European level, which are the green infrastructure and the nature-based solution. Those type of measures aim at providing ecosystem services for society while ensuring a good quality ecosystem. So we can call them a win-win and solution, and it's also shown that they are in general cost efficient. And we, well, to promote this type of measures, there is a green infrastructure strategy at European level, which was adopted in 2013, and which sets objective to implement and encourage this type of measures to be put in place to achieve the objective of the targets of the biodiversity strategy. In terms of new projects, new infrastructure projects in particular, we also have some regulation at EU level which oblige to perform impact assessments. So we have the Environmental Impact Assessment Directive and the Strategic Environmental Assessment Directive. And in case those projects may have impact on aquatic ecosystem, or in particular deteriorate status, then specific obligation from the Water Framework Directive, Article 4.7, apply. And also in case it's in Natura 2000 sites, then we have also some specific obligation that have to be met under the Habitats Directive. And to finish, of course, it's very important to mention that there are legal obligations, as in particular Water Framework Directive, Habitats Directive, EEL regulation, and well, different directive and regulation or legally binding objectives and obligation, and enforcement actions can help to address potential breach and to push for better implementation. So now I wanted to present you a brief overview of the situation in the EU. So
can I just for timing issues?
Yes.
Do you well, a few minutes? Is that okay?
Okay, I will be quick. Okay.
Sorry, thank you.
Yes, sorry. So to be quick, I just wanted to mention that there are some improvements in terms of water protection. In particular, we have seen that there is a better governance overall of water that has been put in place by member states. The deterioration of status of water has slowed down, and there are some hydromorphological measures that were put in place thanks to the Water Framework Directive, and that include in particular amongst the most frequent measure to address continuity interruption, and also that water retention measures and green infrastructure are reported to be implemented in most member states. But there is still a lot of progress that needs to be done, and in particular some major challenge to address. Now we only have 40% of water body in good status, and we know that the main reason are first a slow implementation, insufficient funding, and insufficient integration of environmental policy and sectoral policy. One of the main pressure is hydromorphological alteration. It affects around 40% of water bodies. There is also a lack of integration between EEL regulation and the Water Framework Directive that was shown by the recent evaluation, and not sufficient measures to put in place to restore continuity. So that's an issue. And also very important, I think that some major challenge that will need to be addressed in the coming decades are how to address the very high number of barriers that disrupt continuity. This will be shown also by next presentations. Many new barriers also we know that plan to be built, and in some cases related to other policy goals. And also one issue is how we can improve resilience to climate change by implementing this type of restoration measures. I wanted also to mention the importance of having research projects to support our policies, and in particular mention those two very important projects, AMBER project, but also the FIT Hydro project that you may be aware of, that were funded by Horizon 2020 and that are very valuable to support public policy at the different levels. And then to finish very quickly, just to give you an overview of the different work that are planned in Ecostat and that related to river continuity. So we plan to work on the best practice document on the sediment management in the context of the Water Framework Directive. We also plan to work on the comparison and methodology that have been put in place by member states to set good ecological potential and to improve those methodologies. And also we are planning to organize several workshops on continuity, ecological flow, and hydromorphological restoration measures. And the aim of all this work is to address the main implementation gaps that were identified and to improve the effectiveness of measures to reach good status in the EU. So now my presentation is finished. So sorry if it was a bit too long.
No.
And I would like to say that now I'm looking forward to hear the next presentation about the AMBER project. Thank you.
So do we. Thank you, Jean. Very good. Excellent. That's a very good overview of the policy side from the European point of view. And Martina, you will tell a little bit more about our issue in relation to the Water Framework Directive.
Yes.
Martina.
If I
sitting in Italy, you're prisoned into your own house, I understand.
Yes, I'm confined to 3 years.
Okay.
Can you see my screen?
Mm-hmm.
Can you see my screen?
Yes, we can.
Yes.
There it is.
Okay. Yeah, so I can proceed?
Yes.
Yeah, okay. Hello, everybody, and thank you for organizing this. It's really helpful for several reasons, professional and not professional, to stay connected in this case. So I was already introduced by Wouter. Briefly, I work in ISPRA, which is an Italian governmental environmental institute, and it is also a sort of national environmental agency which networks all the regional environmental agencies, as these competencies are devoluted to regions in Italy. And on top of that, I'm also a co-lead of the Ecostat together with Wouter and Jean and Katarina Vartia from Sweden. And I am the hydromorphology fanatic in the group. So I was asked to give a short overview of how connectivity is included into WFD, what's its role, and how it is accounted for in the assessment and management of rivers. The directive is very concise, but it's a comprehensive piece of legislation which addresses real integrated river basin management, and also the sustainable use of water resources. And it treasures in all the valuable scientific outcome that has been produced in the field of freshwater ecology in the last.
Martina,
hello?
Yeah,
yes?
sorry to interrupt, but I hear that some people have an echo. So can I suggest that everybody who is not presenting turns off the video, so maybe the sound will be a little bit better. Is that okay?
Yes.
Okay, sorry about this, Martina. Just continue.
No, but, I was just resuming the fact that that the Water Framework Directive is very concise, but it includes a lot of scientific outcomes from freshwater ecology and river science.
Yeah.
So as we already saw in the scientific world, but also in the policy network and CIS working groups, is that the Water Framework Directive recognizes the role of hydromorphology as a supporting element, so as a necessary element to sustain ecosystem. And so in every stage of the implementation of the directive, this role is recognized. And we did a lot of work, as Wouter said, in the Ecostat to collect and update all this knowledge about the role of hydromorphology and how to use it in the different stages. And this is now included in a sort of resource document, which you can see here, and addresses a lot of things. But the most valuable part of it is this resource library on hydromorphology, where you can find for every stage what kind of HIMO approach you should use, why HIMO is relevant, and there are examples, there are references, both scientific and related. I'm not going to read this, as hydromorphology, as Jean said, includes continuity as one of the 3 indicators in rivers. So you have the hydrology, the morphology, and continuity. And HIMO is hydromorphology is part of the WFD and is recognized. Then it's also continuity is recognized, and connectivity as well, because continuity is an indicator of connectivity, and the ecological continuum mentioned in the directive is the reference, let's say, target for connectivity. So here I listed all the legal terms of references for this, because you know, there's a lot of controversial discussion on wordings, and if connectivity is inside, I can find the term, and so on and so forth. So the term is not there as connectivity, but it's there as continuity, connection, and ecological continuum, which is more or less the same. In the status assessment, because as you know, the status, the ecological status of water bodies is obtained as a deviation from undisturbed conditions of the water body. So it's as you can see, when pressures grow, ecological status decreases. And by the definition in the WFD, undisturbed condition correspond to free continuity, free movement of energy, material, and organisms. So that means that the directive recognizes that connectivity, when connectivity is high, we have the reference condition. And a slight deviation from high status gives defines the good ecological status. In terms of connectivity, this means that we have to be sufficient continuity in the 3 dimension to sustain native biotic communities. Below the threshold of the good status, there's a red line, because the directive imposes to implement measures to reach the good ecological status. And European rivers ecological status because of hydromorphological pressures that somehow disrupted continuity. Why? Because hydromorphological pressures are designed to put in place some uses, like economical, social, recreational uses, and they are designed to partially or totally block continuity. So they disrupt connectivity, and this in turn can impair and can prevent the achievement of good ecological status. So we have to put these measures to reach good ecological status, and if most of the reasons why we don't reach it is because of disruption of connectivity, measures have to aim to restore connectivity. So the logical scheme is quite simple. We have to use, let's see this example, which is in Südtirol in Italy. They made a lot of weirs to stabilize the channel because of the urbanization close by and because of flood risk and debris flood risk. So the use in general is put in place through hydromorphological pressure. By this, I mean the hydraulic structures such as dam, weirs, levees, and so on, but also sediment mining. And this pressure, in turn, has an impact on continuity, because as I said before, indirectly or directly, the high pressures are impairing connectivity. So we have loss or disruption of habitats, we have impacts on ecosystems, so on the ecological status. And then at the end of this, we also have a drastic reduction of related services. So the same use is suiciding itself. It's unsustainable. This is why we have to keep in mind that consideration of the connectivity and its restoration is so relevant, because we undermine the next future use of the same use. Sorry for the, yes.
Sorry to interrupt again. Maybe you switch off your video, because sometimes still it's a little bit not very good sound. So if you switch video, it might improve. And we noticed that if you switch slide, the sound is a little bit worse. So,
okay, I'll stop video.
Stop video, and then let's see what happens. You have 8 minutes still.
Yeah.
Thank you.
Yeah. Let me. I don't know if you see me. No.
No, it's good like this.
What about now?
Excellent.
No, the slide. Are you seeing the slides?
Yeah, we see the slides. It's excellent.
Okay, great. Because I don't see the control window. Doesn't matter. So I was saying the main reason for not achieving the status is linked to hydromorphological pressures, and so we have to target this with measures that are tailored to restore connectivity when it's viable. Meaning that, for example, if we have a big dam which is producing hydropower and we cannot really release, let's say, discharges or hydrological regime that mimics somehow the natural one, because we need the peaking. And we cannot really restore sediment transport downstream somehow. For then the achievement of the good ecological status is not really viable. And in this case, if we prove that we don't have better environmental options and that society that use it has to be there, the directive through Article 4.3 give us the opportunities to define heavily modified water bodies. So those bodies where we cannot achieve good ecological status, otherwise it would impair the social or economic use. And in this case, the target is from good ecological status to good ecological potential. And the tricky part of it is, and the core of the directive, in my opinion, is to define the good ecological potential and the maximum potential of a water body. And by definition, that's when we put in place all the mitigation measures that ensure the best approximation to ecological continuum, which is, as I said before, a target measure for connectivity. So when we have free movement and three dimensions of water, sediment, and an organism. So that means that we, when we have this best approximation to ecological continuum, flow patterns ensure migration of fish and other aquatic organisms. They ensure appropriate sediments for habitats and sediment transport to ensure also the long-term sustainability of such habitats. And similarly to good ecological status, the good ecological potential is a slight deviation from maximum ecological potential. And so in terms of best approximation, it's not the best approximation, but close to, but still it has to ensure ecosystem functioning. That's the basic part of it. So we cannot have a fish river without fish or without water, to talk really in a banal way. And how do we define the measures to reach good ecological potential? It is very situation specific, but in any case, we know that if some part of processes are impaired, for example, longitudinal continuity, then a sort of family of measures can be implemented. And then the specific measure is going to be selected once we have a sort of operational design stages with all the details of the case. So which is the scale to define measures? We should consider at first ecological continuum at the river basin scale. So for example, if we have the a map with all the pressures, and in this AMBER is so helpful because we need the continuous mapping of barrier. Then we can decide where we can release constraint or where we need to plant some other barrier, unfortunately. So ecological continuum should be considered at the river basin scale, but the measures should be taken at the local scale. So at the river basin scale, we define a strategy for developing economy and society, and then at the local scale, we account for the decision and we design the specific measures. So which measures? The measures are similarly to the natural water bodies, those who mitigate any obstacles to movement of biota, sediments, and water, and that improves the habitats which have been affected by the physical modification of the heavily modified water bodies. Which is the method to define the measures? It's logical, as the flowchart I showed before. It's a DPS higher approach, so cause effect. And this is facilitated by the new CIS guidance number 37 on defining the good ecological potential, which we developed in the Ecostat recently to complement the guidance number 4 on heavily modified water bodies. Endogram, this is a table where you can see the logical path. So you have a driver use. Suppose we have a hydropower, and to put in place that use, we have a pressure, hydromorphological pressure, so a dam. And that pressure has a hydromorphological impact and a physiochemical impact. So disruption of connectivity, so sediments, organisms, and also alteration of flows. And this status defines as an impact on ecosystem, which we call ecological status. And then we have a series of macro family of measures that we can implement in order to define the maximum potential of that water body. And then we can rule out those who are not delivering any results and have the good ecological potential. This is in pills. But as I said before, yes, how many minutes? Yeah?
A few minutes, is that okay?
Yes, it's fine.
Okay.
Yeah. So define type of measure. Of course, this is not a cookbook. This is just a support, a framework to facilitate the selection of the type of measures. But it's clear, as I said before, that then we need very detailed studies on a wider scale on the evolution of the river, on the pressures, on its hydrodynamics, the sediment, the communities, and so on and so forth. But nevertheless, this is very helpful because before this, we were really in a sort of chaos, and that's why we decided to enlarge and clarify some concepts which are valid. I want to stress this, but we needed to clarify also with example those concepts. So as you know, we have two stages. Heavily modified water bodies. So at the wide scale scenarios, at the wide scale, we define scenarios of to reach the use that we need to put in place. So energy, drinking water, and navigation, and so on. And so we decide that certain water body will be heavily modified because there's no better environmental option. And in this case, tools like Cascade, for example, developed in AMBER, can help evaluation of the optimal scheme, the best optimal scheme, like let's say of hydropower, or on the other hand, the strategic dam removal. And then we have the crucial stage of defining good ecological potential that is instead more local. So this means we have to define all those measures that can put in place to mitigate the effect without having significant adverse effect. And then we have two procedures. One procedure is the reference condition procedure. So we remove the measures that only lead to slight changes in values of the biological elements. identify the possible mitigation measure that ensure the subsistence of these BQA values. And then we define, we identify this measure, we define the values for the GP. And on the other hand, we have the so-called mitigation measure approach, so formerly called the Prague approach, where we identify all mitigation measures that do not have a significant adverse effect, and then we define the maximum potential, estimating oh, sorry, yeah, it was the other way around, but anyway, this is the reference condition. So in the mitigation measure approach, we remove the measures that are not efficient, and we obtain the GP, and then we measure the quality elements, and that's where that's the biology that corresponded good ecological potential. It's quite sharp. In the other,
can you round off, Martina?
What?
Can you round it off? 1 minute?
Yeah.
Okay, thank you.
I was just saying the concept is the maximum is where I implement all the measure. The good is where I rule out some of the measures that do not deliver efficient effects. So we have these more detailed flow charts to drive the evaluation of good ecological potential. And in this case, for example, we could use some tools developed in AMBER, such as the predicting the effect of barriers in terms of availability of habitat. And also we can use this tool to assess deterioration to complement traditional methods. So in conclusion, as I said, WFD recognized the role of hydromorphology and the need to restore connectivity or to mitigate its impairment. The directive has promoted a shift from considering rivers as canals, so very simple canals to control, to manage them as ecosystem. And this, of course, implies managing complexity. So we need methodological frameworks and professional, of course, and tools to evaluate and manage rivers in a sustainable way, as I said before. Otherwise, we suicide ourselves. We have no more resources to be exploited in a consumistic way, speaking. And what I want to stress also is that this is not complicated. It's not, we are not, let's say, sadomasochists that create approaches which are complicated. It's just the system. This is complex, and this is a very good quality for the system to be complex, because it means it's working and it's delivering its services. But we need specialists, so scientists in this way, and we have specialists to support us with valuable solutions, like in this project.
Okay.
Oh, so thank you.
Thank you very much.
It was a bit open.
Yes, it was certainly. It was very nice that you ended with this very hopeful message. And it is a really nice bridge to the next speaker in our webinar. That's Carlos, who is heading the AMBER project. We have now 62 people participating. And Martina, maybe you can switch off your screen, and Carlos can switch on his screen.
Yeah, the problem is that I cannot enter the window.
Okay, we can switch off. We can do that.
Switch me off, yes. Yes.
Yeah, 1 moment. And then we ask Carlos to switch on your screen. There it is. And maybe, yeah, there you go. Carlos, we don't hear you yet, but maybe we can unmute him.
Yeah.
It's going down. 1 moment. Is everybody, is it still okay?
Yes.
Yeah.
Oh, there you go.
There you go. We hear you.
Yes, can you hear me?
Yes,
yes.
we hear you now.
Okay, great. So thanks, Ariane. So I think this is fantastic that you guys have been able to put this thing together, and it's very, very exciting. Okay, so what I want to do is to give an overview of the tools for managing connectivity, river connectivity using an adaptive management approach. And this is simply an introduction to the tools that some of my colleagues are going to present later on. Okay, so AMBER, for those of you who do not know, is a Horizon 2020 project that stands for Adaptive Management of Barriers in European Rivers.
Carlos, sorry to interrupt, but you're not very loud. Maybe you can talk a little bit closer to the microphone.
Can you hear me now?
Yeah, that's much better.
Okay. So for those of you who do not know, AMBER is a Horizon 2020 project that started in 2016 and will come to an end in September of this year. It involves 8 universities, 4 industrial partners, some of the largest hydro companies in Europe, 4 NGOs, and also 4 government agencies. So it is very much a truly multidisciplinary project, which involves, as I said, 20 partners from 11 different countries. Okay, so why AMBER? Why is this project being funded, and what is it that we are trying to deliver? Well, AMBER is based on a very simple premise, and it is that healthy rivers are flowing rivers. So the defining characteristic of rivers is that they flow. It means that flowing rivers do not necessarily have to be healthy, but it is impossible, in our view, to have healthy rivers if they don't flow. So start my video. Okay. And this is not new, of course. This is something that was put forward by North American researchers in the 1980s and for many people after that. And I think it's encapsulated very well in the river continuum concept. So healthy rivers, they need to flow. But there is also a very other important reason why AMBER is important, and it is the water crisis. Of all the crises that the Global Risk Report has identified since 2005, the water crisis is year after year up there. It's one of the few stressors which we know is going to be highly likely, and also we know is going to have a huge impact. Okay, so this is going to happen, it's already happening. The water crisis, the need for water is one of the most important global stressors. And of course, in many cases, the way that we make use of water is by building barriers, by building dams. Okay, so here we have a situation where on the one hand, we appreciate that healthy rivers need to flow, and on the other hand, we also appreciate that in order to meet this huge demand for water, we may need to build more barriers in the future. And the climate change is not helping, certainly, and this is some projections from the European Environment Agency, which have been colored according to deviations from the baseline in the next 50 years. As you can see in red, the river flows are likely to decrease precisely in those places in Europe where water is most needed. Okay? That is also not going to help by the fact that we need to improve or to increase the share of hydropower to meet EU energy targets. And what that means is that in the future, the impacts of barriers will worsen. Why? Because water will be needed for other uses as well. So what are the aims of AMBER? The aims of AMBER are 2, is to develop more efficient methods of restoring stream connectivity, and we wish to do so by applying an adaptive management approach, which basically means it's an approach that seeks to maximize benefits of barriers and minimize the impacts. The first thing we need to define then is what do we mean by a barrier, and Martina touched a little bit upon this. In AMBER, we are adopting a very relatively narrow definition. For us, a barrier is an artificial structure, but it's an artificial structure that interrupts or modifies the flow of water, the transport of sediments, or the movement of organisms. And therefore, it means that it will result in longitudinal discontinuity. Of course, it may also result in lateral discontinuity and vertical discontinuity, but the barriers that we are focusing in AMBER are the ones that are going to lose longitudinal discontinuity. And this, which is probably very obvious to you, is actually quite a paradigm shift, because for many, many years, I would say for decades, discontinuity has been colored by the needs of only migratory fish. So what we are advocating in AMBER is a shift from an emphasis only on blocking fish migration, which makes use of this elusive concept called passability, which is taxon specific, to consideration of global discontinuity. And we have defined what we mean by barriers. What do we mean by adaptive management? Well, adaptive management is a process that includes 6 steps. It first seeks to assess the problem. Second, it evaluates the state of the current knowledge. Then it identifies the uncertainties. It implements, it monitors the implementation of solutions, and based on the monitoring process, it evaluates and it starts the process again. So really, it's something very simple, but it has to follow some very specific steps. The first one is that it needs to have a clear objective in order to maximize benefits and minimize impacts. Second, it is a dynamic process. It's not set in stone. It's going to change. It's going to adapt. It will be modified as more knowledge becomes available. And third, it is a process that will test assumptions, will adapt, and will learn. And we do that by using AMBER 2 approaches. On the one hand, we reduce uncertainties by modeling of what-if scenarios, and I will give you some examples, and we also are able, in some cases, to actually test some of these solutions. So the basic question that we put to ourselves was, how fragmented are Europe's rivers? Because restoring connectivity needs first to address this important question, and the answer is simply we don't know. And the EEA recently has acknowledged that continuity is unknown in at least 61% of rivers. So we have a problem, is that we are trying to restore continuity, we're trying to restore connectivity, and we don't really know how much, what the fragmentation of Europe's rivers is. So the challenges here are first, that the number of barriers in Europe is unknown because different agencies, different countries, different organizations call different things. The definition of barrier is something which is not set in stone. For some people, it only means large dams. For other people, it may include culverts. For other people, it may also include other structures. The coverage of the existing information is patchy. It may be very good in some countries, it's not so good in others, and there is also a huge problem of scale. The second challenge is that what we do know for sure without doing any calculations is that it doesn't matter how many barriers we have, something is for certain. There are going to be many more than we can prioritize, that we can deal with. There are many more that we can possibly mitigate against. Our best estimate when we started the project based on regional databases is that there may be between 600,000 to perhaps just under 2 million dams and weirs in Europe. But of course, that wasn't unknown. So what had to be done is to try to provide a harmonized atlas of barriers in Europe. Therefore, the atlas of barriers was the first task, the first output that AMBER worked on. But knowing the scale of the problem will not, on its own, allow us to restore connectivity. We need to envisage and we need to adopt this process that goes from information to knowledge. Data alone is not enough. From knowledge to innovation, we will need innovative solutions. We cannot solve all problems without solutions. We need to be creative and we need to innovate and find alternatives. And from innovation, we need to apply, we need to demonstrate, we need to showcase that some of these solutions are actually going to work. And this is how the different work packages in AMBER were structured, dealing with information, knowledge, innovation, and application. Okay, so the tools we need, we have conveniently divided them into 3 types, DATs, MATs, and SATs, which stand for data acquisition tools that will enable us or are enabling us to collect and harmonize data, to fill gaps, and to make sense of information which is in nature heterogeneous, and in many cases is very disparate information. The second type of tools that we need and that we are using are MATs, mapping and assessment tools, to enable us to assess barrier effects, to predict changes, and to turn information into knowledge. And finally, we need support action tools, SATs, to consider trade-offs, to inform decisions, and to turn knowledge into application based on what-if scenarios. But of course, these tools, they need to be tested and they need to be fit for purpose. Simply because we develop a tool doesn't mean that it's going to work. It's extremely important to actually go out there and try for ourselves. And I will give you some examples of how this has been done. Okay, so let's start with the DATs, with the data acquisition tools. By our latest count, they are recorded in official or semi-official databases, 240 barriers in 36 countries. But as you can see there, you will notice that some countries like France have a lot of dots, Some countries like Italy only have dots in the north. Some countries like Norway and Scandinavia, there are hardly any dots. Does that mean that the density of barriers there is much lower? Or does it simply mean that the databases are not so comprehensive? In other words, how many more barriers are there? And how can we be sure that these dots are not duplicates? Okay? So we know that the global databases which are available massively underestimate the number of barriers because they only consider dams in excess of 15 meters high. And we know that, of course, there are hundreds of thousands more than that. But the problem is that how do we harmonize these different sources of knowledge? So to do that, we developed three data acquisition tools. The first one was the barrier tracker, which enables us to map the location of stream barriers and to compare and to collect information on the conservation status, on whether the barriers are being used or not, making use of citizens. The second is what we call the ground truther, which enables us to account for underreporting of barriers and to derive country-specific correction factors. And finally, we have developed algorithms and we have developed a methodology to try to identify duplicates and to exclude them. And I'm going to just take you through quickly through how this is done and how this can be useful. So the barrier tracker is an app that has been developed for both for the Androids and for Apple, and it has been translated into 12 languages. At the latest count, users all over Europe have recorded over 5,500 barriers, 2,000 users in 36 countries. And this may not seem a lot compared to the number of barriers which are out there, but these users provide us with some essential information which is not available anywhere else, which is whether these barriers are actually being used or not. And because there is photographic evidence, this is something that can be analyzed at a later stage. So we see this as an extremely important and integral part of building this picture of river fragmentation across Europe. The second tool that we are dealing with is the ground truther. And here what we did was to develop optimal sampling strategies to try to compare databases which cannot be compared on the face of it because they were developed in different scales. So what we did is that we sampled 149 rivers all over Europe. In each river, we used the same methodology. We sampled 20 kilometers in 28 countries, and we classified all the barriers that we found in 6 basic types, which are the 6 types which are also reflected in the barrier tracker in the app. In total, as I said, we covered just under 3,000 kilometers. And as you can see, there is the sampling effort was relatively homogeneous. In some countries, it was not possible to cover the target 20 kilometers, but in most countries that was possible. The interesting thing that we found is that it is possible to devise optimal sampling strategies. In this case, we found out that the discovery rate of new barriers would rapidly fall after about 70 kilometers. And the variance of our estimates of density, of barrier density, would stabilize after 250 kilometers. So that's good news. And this is something that we can use for planning future surveys if need be. Once we had applied this methodology, this is what we observed. We observed that on average, there are 0.6 barriers per kilometer. This is the field survey, but there's a huge variation between countries, between 0.04 to 4.43. But the important thing is that on average, the density of the barriers that we found in streams in Europe is about 7.5 times higher than it was thought, that it was estimated from existing databases. And not a single catchment that we sampled was found to be free of artificial barriers. And finally, another thing that was very obvious is that over 85% of the barriers that we detected were actually very small, less than 2 meters. So they are not normally recorded in existing databases. Okay. The third tool that we need to do is how to deal with duplicates. And I'm showing you here some examples of what we are finding. We're finding systematic errors, both within and among databases. You see these are barriers which are in duplicates and which are separated by a fixed distance. Okay, and that's a big problem because, of course, some of these barriers are developments over existing ones. Some of these databases may be a bit old in some cases, and nobody, as far as we can tell, has actually bothered to check them. So duplicates is a big problem that we need to deal with. This is another example. You can see here that's the same weir, which is present in 5 different databases, 1, 2, 3, 4, 5. And it's exactly the same weir, and it's very, very close to the road. So how do we deal with this? Well, we deal with this by looking at distance to nearest neighbor. And the task here is to characterize the distance to nearest neighbor of true records and to characterize the distance to nearest neighbor of non-duplicates. And then based on that, we determine an optimal exclusion radius that tries to do 2 things: to minimize the rate of false positives, i.e. duplicates, and to maximize the number of true positives, i.e. to maximize barrier detection. So this is the empirical data derived from this approach. This is the distance to nearest neighbor of true positives. And depending on which database we use, you can see that the median may range between 108 meters if we use all the barriers that were validated in the field in Europe, to up to 742 meters as a median for particular small catchments. Okay, so this is the empirical information that we have for distance between barriers which we know are true positives. They are not contaminated by duplicates because this is fresh survey data. If we now look at what is the situation for known duplicates, these are barriers that we know for sure are duplicates, and we have looked at over 3,000 of them. And what you see here is that for different countries, this is the cumulative distance to the duplicate point versus the proportion of total. And I think you will agree with me that with a few exceptions, most of the countries, they cluster around this upper left corner here. And in fact, if we look at the 80% power, we find that 80% of the duplicates will fall within a 445 meter radius. So with this information about the distance to true positives and the distance of true duplicates, we can apply filters to try to get rid of duplicates in the database in a way that is sensible and that is efficient. Finally, or the second type of tools which I mentioned, which I'm going to explain very briefly, is our MATS tool. This stands for Mapping and Assessment Tools. They're going to be covered in the next talks. We have an eDNA toolkit that seeks to detect discontinuities in river biodiversity caused by barriers based on samples of water. We have a fish habitat modeling and mapping, which seeks to quantify fish habitat and predict barrier impacts based on reference fish communities. We have a sediment dynamics modeler, a cascade approach, which seeks to assess barrier impacts on sediment dynamics. And finally, we have a tool that enables us to map ecosystem services and identify those ecosystem services which are most affected by dams and reservoirs. And this will be explained by our colleagues later on. There are other map tools, and I'm going to just mention 2 of them. One is the rapid barrier assessment, which is a way that enables users to quickly and efficiently assess whether a barrier is likely to pose a problem for fish without too much of a detailed measurements. We also have a fish swimming performance assessment that enables us to assess the swimming performance of weak swimmers and neglected species. And finally, we have also developed approaches to try to gauge public attitudes to dams and reservoirs in Europe. And I'm not going to present this. I'm simply going to very briefly present the approach to model densities and the approach to come up with more holistic metrics of fragmentation that can be applied across Europe. So the barrier density model was developed by the Italian colleagues Alpolini and JRC, by Barbara Belletti and her colleagues. And basically what they try to do is to use machine learning to, based on high quality data sets, to extract algorithms that based on the high quality data sets that take into account 4 parameters: hydrological parameters, morphological parameters, land use information, and human pressures. Okay, so based on these rules, what Barbara and colleagues were able to do, and this is preliminary data, is to produce the first complete map of barrier density in Europe that is consistent and harmonized. And as you can see there, in this particular approach, we can see that on average, they may be 0.13 barriers per kilometer. but different models will produce different outputs, of course. And you can see that some areas of Europe are relatively free of barriers, and but some areas are hotspots of fragmentation, where river continuity has been lost much more than average. And it's very, very important to point this out. These models are not going to be useful at a local scale. They are useful at a pan-European scale. The emphasis here is to compare countries, to compare broad regions. This is not a substitute for management at the local scale. Another tool that we have developed is to enable us to come up with perhaps a more holistic, more meaningful metrics of river fragmentation. The obvious one is barrier density. I'm going to show you data for France, which has been color-coded depending on the number of barriers per kilometer. But of course, barrier density doesn't really provide, is the minimum, but doesn't really provide an indication of how fragmented the river is. A better metric of fragmentation may be what is called barrier-free length, i.e., what is the maximum or the median or the minimum distance that a particle, an organism, or sediment could travel before intercepting a barrier. And red means bad, and orange here means good. And as you can see, the case for France, which is heavily modified with barriers, most of them are very small. All the central part of France has very, very small values of barrier-free length. Another metric that my colleagues are working on is the so-called dendritic integral connectivity index, which takes into account the number of neighborhoods, the number of, neighboring watersheds that a particle could move to or an organism could move to. And again, that will give you a complementary, but in some cases, different information. At the end of the day, what is important to realize is that different metrics may be needed for different purposes. We don't think there's going to be a single metric of fragmentation that we can apply across Europe willy-nilly, and that is going to solve our problems. I think it's important to realize that depending on the task, different metrics will need to be used. And finally, I just want to mention two tools, which are the support action tools or decision support tools. One is going to be presented by my colleague Jesse Hanley, which is the barrier planning decision support tool that seeks to optimize environmental socioeconomic trade-offs associated with barriers. And I'm just going to show you some results of the second tool, which is a barrier prioritization tool that we have recently developed. So this was ground truth in one small catchment in Wales. It's the River Avon. And we believe it's the only, or one of the few times where a whole catchment has been thoroughly and exhaustively sampled, not just for artificial barriers, but also for natural barriers. So there were 256 kilometers with a team of volunteers. This catchment was surveyed on foot for, I think it took about a couple of months. And the people discovered there were 399 artificial barriers, some of which you can see here. In most cases, they're quite small, but also there were 520 natural barriers that may also cause discontinuities for some species. The natural barriers are highlighted in the green. The artificial barriers, they are highlighted in red. Now, what we did was to ask a very simple question. If there were no barriers, what will be the connectivity of the Avon catchment? And of course, when barriers is 0, the connectivity is 1 by definition. Okay? So if we use barrier-free length as our metric, you can see that as the number of barriers increases, and this is empirical data, the connectivity drops very rapidly, but it drops very rapidly within the first few barriers. In this particular case, 22 barriers are enough to cause a 50% reduction in connectivity. And what does that mean? It means that removing a few barriers here and there in heavily fragmented rivers is probably going to be useless. And it also means something, if we are serious about maintaining connectivity, prevention is better than cure. We need to ensure that those rivers which still have high values of connectivity are not fragmented by just a few barriers at the very beginning of this curve. There's no point in doing restoration measures. Well, there is a point that is going to be very expensive in this part of the curve. I think that emphasis should be invested in preventing these rivers from sloping down this curve. Okay. And finally, I'm just going to show you some examples, which is not modeling. This is empirical data. This is one of the AMBER case studies. Is the Putes Dam in the river Allier in France, where the people there are police, EDF, and the CNSS, and others have applied adaptive management in the operation of the dam. For those of you who do not know, the Putes Dam is, or was, 17 meters high, and it created a reservoir which was roughly about 3 kilometers long. And it was one big, big barrier for the migration of Atlantic salmon. In fact, it has been estimated that this only barrier was blocking about 42% of the best salmon habitat, spawning habitat in the River Allier.
Carlos, how long do you need still? Because we're
1 minute.
over time. Huh? 1 minute? Oh, okay.
2 minutes. Very few rivers were actually able to overcome the dam. So just to sum up, what the people there did was they played with flows. They adjusted the amount of water that they could divert over the spillway. And what they did is that they radio tagged the fish to see how changes in the operation of the dam would affect the movement of salmon, the movement of smolts. And this is the data. Under normal conditions, smolts took on average about 3.6 hours to cross. Maximum was 2.7 days. And when the reservoir is lower, it's the other way around, what you find is a significant decrease in passage time. So it's not going to be as good as when there is no dam, but it's not going to be as bad as when the dam was creating a 3-kilometer reservoir. So this is the retrofitting, this is the new Putes Dam, which what they are doing as we speak is that the dam is going to be, or is being lowered from 70 meters to about 4 meters. The reservoir is changing from 3 kilometers to 300 meters, and while still producing roughly between 80 and 90% of the electricity that it used to generate before. Okay, so this shows that situations are sometimes not black or white, that it is possible to retrofit existing dams with better technology, with more efficient solutions that can still generate electricity and cause a fraction of the impact. And finally, just to sum up what the AMBER tools, what the take-home message will be from our tools, and it is to point out that Europe has the most fragmented rivers in the world, that most barriers are small and many are obsolete, that there are many more barriers that is going to be possible to mitigate for or against, and therefore that to restore connectivity, tools are needed to prioritize barriers for mitigation or removal. And simply to say that on the 15th of May, we will launch our magazine. Some of the tools I have described and that my colleagues will be described there. And also that you are all invited to come to our final AMBER Hydro event in Lisbon on the 29th of June this year. Thank you.
Okay, thank you very much, Carlos. That was a very quick overview of a very, very large project. And now, luckily, we have a few more people who will present some more details about some of the tools that you were talking about. And we start with Richard, who has something to say about eDNA. Richard, can you start? And maybe you can try to be a bit short so we can win a few minutes to be in time for the end of this webinar. Richard, are you there?
Might be on mute. I can see if I can unmute him.
There he is. I see him already.
Oh, you do?
We don't hear you. So, now we hear you.
Oh, great.
Okay. All right. Just to make sure that. Tell you what. Here, I'll.
We have 63 people listening to you now.
Okay.
Full expectations.
All right. Should we? So can you see my screen now?
No.
No. Okay. So in that case, I'm just going to cut that out.
So are people still, does everybody hear everything well enough? This is a moment where you can shout and make suggestions. As mentioned, we will come back to questions that are being put forward via the chat box. You can get the chat box on your screen by clicking on chat. It's in the bottom of the screen. And Wolf Jan, you're saying I hear everything fine. That's nice. That's good to hear.
You got a thumbs up for Walter?
thumbs up from Wouter, so that's good. And now, Richard.
All right.
Yeah? Are we almost there?
I hope so. I'm very sorry about that. I'll try and keep this nice and short. Yep.
Yeah.
Okay, so you can see the screen?
No, we can see you, but
Okay.
Okay, share that. You click that, not click that.
Yeah, yeah.
And then is the green one.
Yeah, yeah. Okay, sorry, I'm gonna.
Yeah, yeah, okay.
well, we don't have webinars every day, I guess. There we go.
Yay.
You can see it now.
Yeah,
Okay.
go for it. And win a little bit of time, please.
All right. Yeah, yeah. I'll try and keep this really nice and quick. So, this talk is about the use of eDNA to assess connectivity and fragmentation. So, in brief, environmental DNA refers to the fact that organisms continually release their DNA into the environment, and we can collect that DNA and measure it. And this is an approach that has been increasing in use in recent years. And perhaps the most important thing to stress, and the take-home message of this, is eDNA is not a tool, eDNA is not a technique, eDNA is a naturally occurring phenomenon, a thing that is in the environment, and we can measure it using different tools and different methods. And that's what I'm going to talk about now, is the options that we have for measuring environmental DNA to assess fragmentation. So you can break the measurement or the toolkit that we're going to be discussing about down into several different sections. So the sampling of water, the extraction of the DNA, and then the measurement of the DNA inside the lab. For this talk, just for simplicity's sake, I'm only going to concentrate on the first two components of that. And that's really because from the point of view of assessing connectivity and of looking at barrier management, the most crucial decisions that we have are in those first stages. So there's actually a multitude of approaches that people have made for measuring eDNA, different volumes ranging from 15 mils. 1 litre is kind of the most common volume that people will take out of the water to purify eDNA from, but it can go up to 30 litres. And then there's, on top of that, there's the number of decisions just multiply. So what we have developed is a really pragmatic approach to sort of decide on what are the most appropriate tools for assessing fragmentation and connectivity. And perhaps the first most important thing to remember is just a property of ecological systems, of communities, which is that they're highly dispersed. You'll always have these very abundant taxa, and then you'll have individual organisms that just occur, you know, there'll only be 1 or 2 of. So if we were able to take a cross-section of a river and just sample all the eDNA in there, we'd find that we'd have an abundant amount of eDNA, and then we'd have these other individuals sort of that only pop up once or twice. And then if we subsample, which we have to do out from necessity, we'll find that there's certain patchiness in the distribution of that eDNA. And that means that we have to collect replicates to get a true picture or a representative picture of what's really there. And so there's a trade-off between the cost and logistics of collecting numerous replicates and getting sort of the best representation of the community. In addition to this, there's a lot of other properties of rivers that I'm sure that you can appreciate. There's considerable variation seasonally in the amount of suspended sediment that's in a system. So if you're using filtration to collect material, that's really going to have an impact. There's variable water depth, mixing, and also rivers travel in one direction, so you'll get downstream transport of molecules.
1 minute.
Yes.
That's it.
Oh, sorry, Arian?
No,
Okay.
just, I was trying to say very subtly 1 more minute.
1 more minute. Okay. Well, all right then. So, okay. So another requirement is the method must be portable. So, you know, like AMBER isn't about just looking at one big dam. It is about looking at dams and other barriers, weirs that are distributed throughout a system. So you have to sample at numerous points. Also, you want to sample a system repeated times because these systems change. And so essentially, we've developed a method that is ideally, it's about portability and it's about being lightweight, so you can carry it to anywhere. And so it either uses syringe filters, or else we sort of would favor using some sort of portable peristaltic pump. And there's also an importance on keeping the field, your field work nice and clean through the use of gloves, bleach, and also there's an emphasis on having negative controls. I think I will end the talk just there. So essentially, there's this decision tool that you have of looking at your system to decide on the amount of samples you need to take relative to the flow rate of the system. We'd recommend as a minimum taking 3 replicates, but ideally more. And a volume of 1 litre seems sufficient if you have sufficient replicates. I'll leave the talk there. Thank you.
All right, thank you very much, Richard. And I'm sure that if people have more questions, they are very, you're open for more information and support, I guess, right?
No worries.
Yeah, okay, great, thank you. Then we Piotr Parasiewicz from Poland and part of AMBER. I know, Piotr, you're a great presenter and you can talk for hours about this issue. And so I hope you can keep it within 10 minutes.
Hi, Parasiewicz, that's the right way to say that.
I said that, didn't I?
So yes, I'll try to keep it short. My talk will be about the part of the tools that we developed that are dealing with a little bit of a different problem that it's usually being done, namely with the fact that when you put the barrier, it actually affects the, sorry, I got stuck. You see, oh, sorry, you don't see my screen, right?
No, we don't see your screen right now.
Now you see it?
Yeah, there it is.
Okay, good that it stopped me. Okay, so when we talk about barriers, we frequently forget that they don't only block the connectivity itself, but they also have impact on the habitats up and downstream. So, and it's maybe more well known that there are impacts upstream where we change the river into a pond environment, when we have compared to the free-flowing rivers, a higher depth, lower velocities, increased siltation of a substrate, higher temperatures, lower oxygens very frequently, eutrophication, and that is causing the shift in vegetation, bentost, as well as aquatic fauna. And with regard to aquatic fauna, we have already an evidence, and we can imagine that when we turn the river that you see, that is this upland river like you see here, it has a fish community that is dominated by river fish, by rheophilic fish, so-called, and the impoundment, then all of a sudden we find out that the shape and the constitution of this community dramatically changes, and it's becoming pond, because it becomes pond environment, so it's dominated by pond fish. Little less maybe known is that the habitat also downstream is dramatically changing. We have fluctuation of depth, velocity, temperatures also connected with this, what is happening upstream. We have a blocked sediment, riverbed erosion, frequently dewatering and mortality that is connecting to it. Also, and we found it out in our recent studies on Vistula River, fish community structure also dramatically changes from dominated by riverine fish to into generalist dominated fish community. So similar effect, maybe not that strongly, but also similar effects that causes this dramatic shift and movement of the communities into different types. And it's caused by what? By habitat modification. So that's what we are trying to investigate, the modification of habitats that would lead to these changes, and basically invest and try to find out the ways to mitigate the impact of barriers when we are defining habitat changes up and downstream, try to develop with the tools the mitigation scenarios, also compare and select tools that are helping us to compare and select the right scenario to mitigate for those impacts. And the first and basic step, and Martina was talking about it, is to establish a benchmark, establish a reference to which we can compare those changes. And what we are trying to do, because this is a pan-European project, was to establish a benchmarks that will be valid for the entire continent. And for this purpose, using the pan-European data, our team created those structures of the fish communities that we can find across the Europes. And through the statistical analysis, we found out there are 15 types of those fish communities. They consist of, in order to build this model, we created, we basically grouped the species into habitat use guilds. So we have this high rheophilic intolerant species, which is mostly trout and salmon, so salmoniid species, divided into those groups, and then investigated what are the expected proportions of those habitat use guilds at different water bodies that we find out in Europe. And the next step, once we had these 15 communities, was to figure out where do they actually occur. And we created these maps that provide us with information in which portions of Europe you can find which distribution of the communities, and therefore you would expect habitats that support those communities. Those are the habitats that occur without the barriers. This tool, of course, is a benchmark for investigating the impact of barriers, but also you can invest the impact of, let's say, environmental flows or river regulation and other type of modifications. So this is one of the very important tools that we created in this project, and we believe that it will serve in the future assessment of ecological potential and ecological status. Here is one of the examples of how this tool could be used, and we developed a so-called conceptual model of barrier impacts on upstream fish habitats. And this model is taking into account those different types of water bodies, as well as different types of barriers. And based on the fact that we know what we know about changes in the depth, velocity, substrate, and so forth, we estimated for each of those river types how much habitat would actually be left in the impoundment. And it turned out that in the alpine rivers, for example, we would expect beyond the dam, we would expect only 11% of habitat left. Whether if we have a culvert, we would expect maybe 73, and other places almost up to 90% of habitat left. This will be different in Mediterranean highlands, where almost 59%, or lowland Atlantic rivers, 63% of the habitat will be left beyond the dam. So that's already one of the important aspects. However, we need to consider that this model that I have shown you before considers the barriers that maintain the high ecological potential. So have a fish passages, all the mitigation measures that were possible. If we assume that most of our barriers don't have those mitigation measures and correct for that, we are observing a picture where in alpine area, we should assume that there is no habitat left beyond the dam. On much more smaller quantities of habitat area is being left beyond the dam. To investigate the habitat downstream and also as well as upstream, there are also more sophisticated model, and one of the model that we applied here and used is the habitat simulation model. and we use Mesohapsim model for this purpose that allows us to map the distribution of different features in the river, observe the species behavior and the areas that are preferred by them. Then the maps of the features can be translated into maps of suitable habitats. And the quantity of this habitat serves as a tool for investigating and simulating all possible management scenarios and observing what is happening if the flow in river is increasing, the habitat might be increasing. What is if we introduce the climate change and so forth. This is a tool that exists since longer time, and one of the key obstacles in implementing it across the continents was the effort that was necessary to gather the information, because the information about the fish using the habitat has to be gathered at the scale of the fish, so much smaller than the scale that we are considering for the watershed management. Therefore, one of the key elements that we had to address here, developing this toolkit, was the way of collecting the data in a more sophisticated way or more effective way. We used a lot of remote sensing for this purpose, drone pictures, movies, terrain models, spherical photography, bathymetric surveys, field survey apps, and so forth. So this has been addressed, and specifically, we've recognized that the large rivers are providing a lot of difficulties in this area for the very same simple reason that they are large. And we are much smaller if we are on the boat in this river, in the river like Vistula that you see here, than walking in the little stream. So we can see much less. Therefore, here the use of drone imagery was a basic tool that allowed us to create those maps with bathymetric data, where we can identify relatively quickly the distribution of different habitat units or hydromorphologic units, as we call them. So we have UAV photos, bathymetry, and hydromorphologic units are coming out of it. Another important element that creates particular difficulties, specifically on the large rivers, is a substrate, because in a small river you can relatively well quantify it. In the large river, it's getting difficult. For the open areas, the colleagues have developed the toolkit that allows us to observe, use the drones to observe and define the photo sieving from the drone pictures. And this movie is showing it here, maybe it's a little too loud. So different types of imagery as being applied and collected with the drone technology from nadir and from also oblique pictures, as you see it in a minute. And with this information, we can compute and perform semi-automatic photo sieving. So get very detailed information on the grain that occurs in the river. It's a very important element of river habitats. This tool has its limitation. First of all, you have to see through the water. It's the best, like in this case, in the areas that are relatively dry. In the areas where it is not so easy, on the large rivers like Vistula, it's getting much more difficult. So another toolkit that we've developed in our model was a model, statistical model of habitat distribution. We used the data that were collected from many countries in the world, data on habitat analysis when we observe the distribution of hydromorphologic units and the distribution of the habitats, of the substrate, I'm sorry, and use neuronal network model to define the distribution of different substrate types. So we basically, for any river, we measure depth and velocity, and we can tell you what the substrate will be there. And maybe vice versa. If you observe the substrate, you might.
To interrupt, you have 1 or 2 minutes still. Is it?
I'm almost ready. Yeah, I'm getting there. So with this information, we can create those habitat models that tell us not only about the distribution of the habitats in the morphology in the river at different flows, but also for different gills that you have seen before, how much habitat will be suitable or not suitable. This information is then turned to the vehicle for further analysis, which are habitat rating curves that you have seen before for different species, for the communities, and as well as the information on different areas in the river, how much habitat they actually contain. For example, here, Włocławek impoundment for rheophilic fishes basically do not offer any habitat suitable, whether the area directly downstream of the impoundment, very little, and further downstream, we already have higher amount of habitats for those intolerant fish species. All that is then turn into the very much more sophisticated mathematical analysis when we analyze time series, perform different simulations, simulation of dam removal, simulation of climate change, and create different scenarios. And then plot the results of this analysis. We plot in these diagrams that we call restoration alternative analysis. When we plot so-called habitat stress days alteration. These are days when we have a very strong deficits of habitat. We plot alteration of habitat structure, and we can compare different scenarios, like in this one example from Poland, when today's situation, this is scenario 2.8, is compared with dam removal situation, with flow augmentation, with situation after the climate change, time series modification, and very easily we can find out which scenario is the best for the future. In this particular case, it was dam removal. So this is the bunch of tools that we are providing. We provided also a toolkit for the users. So AMBER field data collection manual that tells people how to do it actually, how to perform the data collection in the field, and the data analysis is of course provided in different documents. So that's what I was ready to present. Thank you very much.
Okay, Piotr, thank you very much. The tool, the guidance that you're mentioning, it's going to be also on the website soon when we deliver all the products of AMBER. So that will be available for everybody pretty soon. Can I ask Simone to talk about sediments modeling? Simone, are you there?
Yes, I'm there. Good morning.
Good morning. 10 minutes?
Yes, I will start just sharing the screen. Okay, you should be able to see it. So this morning I'm going to speak in this talk about the cascade model. That is a model that we have developed over the last year at Politecnico di Milano, and now I moved to University of Padua, Department of Geoscience, for analyzing river sediment connectivity and management, and we also apply and further develop this tool in a case study for AMBER. So very briefly, the intent of this presentation is to tell you what is it about this toolbox and how it can help river management issue in general. So we all know that rivers are deeply interconnected. This holds for ecosystem process, but also for sediment. And sediment create a continuum from the headwaters to the delta. And it's very important to understand when we speak about connectivity, not only the amount, but also the frequency, the provenance, and also the typology of sediment that you can get in any reach of your river system. In literature so far, we are mostly able to represent decently well sediment transport at the reach scale. So from few hundred meters to 10, 20, 100 kilometers, but our ability to understand how sediments are linked and connect at the basin scale and network scale is still, let's say, at its beginning. So there are tools over outside there where you can start to have this type of assessment, but our ability is still pretty limited. But this is very important because, as we all know, any kind of alteration in the system, from channel maintenance to riverbed mining for construction or other reason, deforestation, damming, all this kind of impact affect sediment connectivity. And this is happening at the basin scale. And these in turn affect also all kind of ecosystem process, from loss of fertility in floodplain to impact on life cycle of fish connectivity, for instance. So one thing today I'd like to underline is that Cascade is a network scale approach. So one of the most important thing is that when we are looking at basin scale perspective, kind of alteration like deforestation, dams, or bed mining, we can able to assess the impact at the local scale with many toolbox or with many approach in a decent way. But it's very important also to be able to understand the cumulative impact. And Cascade allowed to do that, at least for sediment connectivity issue. So how different barrier, how different land use scenario or bed mining scenario could affect river system at the network scale. So Cascade is a model that provide information for any reach in a system about how much sediment is passing by, where is it coming from, and what type of sediment is coming. And has been used for management type of case study that I will very, very briefly show this morning to you, or more than show, I will mention to you. It's a toolbox at the moment that is available on our website. And very briefly, the system works like you segment in hydromorphological homogeneous reaches your river, and then you route the sediment having information on hydrology and on some geomorphic and channel geometry information. And you can add in any part of the system the type of alteration that can be natural, like closer to alluvial fan or debris flow, and can be anthropic, like dam or deforestation action. Cascade has been developed, designed to run even in a situation where you don't have a lot of data. You need a DM. You can have some information on channel geometry, even looking at Google Earth or other kind of orthophoto. And you can use distributed hydrological model, even the one available worldwide, to have some estimate of water discharge. Obviously, now I'm not going to the detail about how the system works. I just want to show you a couple of examples because I see that we are short of time. So one example is in the 3S, in the Mekong River Basin. And we are speaking about the 3S Basin. So here is the Mekong Delta, and the 3S Basin is one of the majority source of sand for the Mekong Delta. And in this system, there is a large-scale dams development plan that is happening, and it will happen for the next decades or so. And obviously, it's a basin that is large and poorly monitored, especially in terms of sediment transport information. So we have applied Cascade to have a sensitivity analysis of what could be the connectivity patterns in this basin, and now we can use this information for strategic dam planning scenario. So what I mean is, this is the system here on your right. Each of these dots is a source of sediment and is a segmented reach with specific geomorphic feature. And then we have an exercise of sensitivity analysis where we hypothesize a range of sediment supply plausible from each of these sources. And we have thousands of simulations that are these gray dots here that provide information at the outlet. That is the sensitive information to have data on how much sediment will reach the Mekong Delta, in terms of D50, so grain size, what kind of sediment, and in terms of kilograms, so how much. And as you can see, we have information on grain size and fluxes at the outlet measured in the field. And so only few simulation amongst the 1,000 that we have simulated match the observed simulation at the outlet. So this is a way we have used to calibrate cascade also in a very data scarce environment. And so we were able to determine the sediment flux in this big basin even with few field data available. And then we have used this information to make an exercise of management. What you can see here in this graph here, this is the sand flux that is getting to the Mekong Delta. And this is critical to survive of the Mekong Delta, where 20 million of people live, and there is a valuable land for agricultural production, and not only. And here you have the generation. So how much hydropower is generated by a portfolio, so a combination of dam in the basin. Each of these dots that you see here is a combination of dams in the basin. So different scenario of how you are going to build a dam. The square point that you see here is what is happening in reality and what is planned. So nowadays we are here. So we just built this dam here, that is the LSS2 dam here at the outlet. So we are stopping around 80–90% of the sediment to the delta, posing critical threat to the delta, producing around 50% of the sediment that is planned from now on to the next 50 years. And then we play just switching on and off different combination of the dams in the basin. And we wanted to look what is the frontier of optimal solution that are these circle point here. And as you can see, in an ideal world, we were able to find a combination of dam that trap only 20% of the sediment to the delta and produce the same amount of energy that we produce in the future. And as you can see, there is also a nick point here where probably showed that probably is worth to exploit this basin until 70% of the planned hydropower energy. After that, the trade-off is no more valuable, and probably we should switch to alternative type of energy production like solar system or other kind of system. So this is an example where we apply cascade and sediment connectivity information to a strategic dam planning problem. The second case study, and then to finish, instead is in the Vjosa River network. The Vjosa is a stunning braided system, one of the few still remaining in Europe, in Albania. And in this area, as most of the Balkan area, there is severe hydropower development plant in the next future. So we wanted to study this case study in the context also of AMBER to see how different combination of dams could affect the connectivity of the system that is so important to the survival and to the maintenance of incredible ecosystem of hotspot like the braided ridge that you see here in the D, so in this lowland part in the Vjosa River system. Again, also here we provide a validation of cascade. So we have applied with the distributed hydrological model that were available, DEM were available, and we collected in the field information on grain size here and there across the basin. And also we have from a study from the Bocconi University in Austria, estimation of bed load here in the downstream reach in the Pocem, near Pocem. Now, I don't want to go into the detail of the validation. I just want to highlight that with few data, so grain size sample, grain size distribution, superficial one across the basin, plus information on bed load in POCHEM, we were able to decently estimate and calibrate the cascade information, cascade simulation, and the cascade simulation matched pretty well the data that we collected into the field, either in terms of bed load transport and in terms of grain size validation. So we can also show how the finding go from upstream to the downstream and match the grain size distribution that we collected in the field, that are these green line that you see in this graph. But I just want to finish telling you how we have used this information in this case study. So it's very well known in Europe and also in US that braided river system, especially when they are affected by alterations such as sand mining or the construction of dams, so you have a reduction in terms of sediment, they simplify the river type and they became first wandering and then single channel in size river. This trigger a number of problems. Riverbed incision obviously destabilize banks, reduce the level of the water table, and threat all kind of habitat ecosystem that were maintained in a braided style. So it's very important to understand when you have the risk to shift from a braided river system that is an hotspot of biodiversity to go towards a single channel in size river system. In literature, there are some thresholds that are well known to divide when you have the condition for the existence of a single channel compared to a braided channel. And these are mostly based on information that relate to sediment transport. So D50 sediment concentration that is created, that you can see here, from sediment fluxes and sediment size. And what you see here, we have classified each reach of the entire system in single channel and multi-channel, that are the blue dot, circle dot. Single channel are the red dot. And as you can see, we have also defined a threshold that pretty well discern in the current condition, using information from cascade simulation to have information on D50 and sediment fluxes to discern between single channel and multi-channel pattern. And then what is...
Can I ask you, does it take a long time still, Simone?
1 minute.
1 minute, okay.
Really 1 minute. And what you see in this slide is that if we simulate, so this is the current scenario where we subdivide braided channel from single channel, and if we look at future scenario with dams, so we have hypothesized a reduction in sediment of the 50%, all these blue line below the red line are likely to experience a shift from braided to single channel in size system that will trigger a chain of ecosystem issue and also management issue that are well known in the literature of fluvial geomorphology. So with this, I just want to conclude that we are now able to have network scale quantitative assessment of sediment connectivity, and we can also link sediment connectivity to fluvial process to assess river sensitivity to support river management in general. That is it. Thank you for your time.
Okay, thank you very much. That was very, very helpful. Thank you very much, Simone. We'll continue now with Jesse. Jesse, are you ready to tell us about the decision support tool?
Great, thank you.
There you are.
Hi, okay, so I'll jump in. I'll try and be brief as possible. So, sorry, can everybody, I'm not sharing my screen, sorry.
No, we'll see. We are seeing you.
My bad.
Yeah, there you are. 64 people listening to you, Jesse. Go ahead.
Lovely, lots of pressure. So welcome. Okay, so I'm going to discuss the River Infrastructure Planning Decision Support Tool. So this is work I've been doing with colleagues at IBK, hydropower company in Germany. So I don't want to underestimate the amount of effort they put into this. So really I think kind of picking up from what Simone was saying is what this tool is really, I think, powerful at doing is handling cumulative effects of barriers. And I mean, another way to think of it is in more broad terms, interactive effects. So you can have interactive effects in terms of how barriers affect longitudinal passability, how they affect hydropower, and how they affect various other types of benefits or impacts that we might think of on the system. And so I'll try and elaborate on these kind of points as I go through. But really the overall aim here is we've got basically a whole bunch of data on barriers. It could be, the barrier type, the amount of passability, how much it would cost to replace or remove these things, all sorts of information like that. We've also got a whole bunch of information on, say, river data, river length, position, hydrology, etc. And so what we're trying to do is take that sort of basic types of information. We're going to plug that into our model, as well as kind of our different range of socioeconomic goals that we want to consider. And what this tool will then try and do is sort out which kind of barriers should I kind of remove, modify, replace, or even maybe even possibly add in new barriers to optimize my different goals that I want to achieve, which I'm also calling key performance indicators. So what this model will do is kind of take all the different things, sort through them, figure out the best combination of barrier projects to implement, and then kind of outcomes an optimal solution, if you will, to achieve the socioeconomic goals. And so it'll come up with a kind of a spatial map of different barriers to go after, as well as the different, how well this particular solution will match up on my KPIs. And so I'll kind of jump in. So what are we talking about for KPIs? Now this is kind of a little bit specific to what we were dealing with in our German case study, but it could be broadened out as well. So what we were dealing with is maximizing river connectivity, which is measured on a 0 to 1 scale for the whole basin. We've got, so 1 would be a fully connected river basin, 0 would be a completely disconnected river basin. We also want to kind of maximize hydropower generation. So that's a benefit we're getting from some of these barriers. We want to minimize costs. There's lots of different costs we could think about. So from barrier modification, mitigation, removal, we have the engineering works to do that. In our particular case study, waterborne transport, so shipping, was a really key thing we wanted to maintain in our particular case study. So we also had to consider the cost of that and how modifying these barriers would affect river transport. We also have to consider the cost of installing hydropower turbines. We could consider also hydropower revenue if we want. And what's not on this list is all the other stuff that you could have for any particular case that you're trying to deal with. It could be recreation. It could be it could be your water supply, your food supply, all those sorts of things that were mentioned earlier. So main inputs that we're dealing with, well, we need to know where the different artificial structures are. We need to know some basic physical design characteristics like height, elevation, installed hydropower capacity, that sort of stuff. There's lots of information on hydraulic data, flow volumes, natural water depth. We have to know about the passability. I'll talk briefly a little bit more about that. We need to know what are the available options that I have in front of us. And we need to know what the cost of doing these different options are, the cost of hydropower installation, and we need some information about what it'll be for shipping, based as a function of water depth. So those are kind of the same main key inputs that would be going into this particular model. So a little bit elaboration on passability. You could just say, you know, a particular structure has a certain passability and that's it. So passability 0 would be not passable. Passability 1 would be a fully passable barrier. And then, you know, say 0.5 would be something in the middle. What we try to do is a little bit more elaborate system is try and relate this to the type of structure and whether or not they have fish passes or not, and what the actual head difference is for the particular barrier. So for example, if you have no fish pass, if the head, which is the difference between the water height above and behind, in front and behind a particular barrier, if it's less than say 0.2 meters, fully passable to fish. If it's greater than 0.2, then passability drops off to 0. We can think about adding a fish pass, which will, you know, increase those passabilities. And then locks, maybe, you know, just have a standard passability value. So you can come up with, again, more elaborate passability scoring systems if you like, but this is just one example. So what was really particularly novel about this particular tool is how we model river connectivity. So I wanted to point this out. So in most systems, they make a very simplifying assumption that you have a fully dendritic river network, which would be the kind of the figure on the left there, where there's basically, to reach any particular part of the river, say from below barrier A to barrier, to the part above E, there's one single path. There's no, you know, you can only reach it in one possible way. Now, the fact is, in a lot of industrialized river networks, particularly throughout Europe, you have stuff where it's multi-threaded, so the figure on the right. So what you might have is multiple barriers aligned in parallel. Maybe one's a weir that's kind of pushing water over to the left, and then there's maybe a series of hydropower stations or some locks, etc. What this creates is multiple pathways for fish and other aquatic organisms to reach different parts of the river network. So this really kind of complicates matters, to say the least, and it requires kind of new novel ways of modeling connectivity. So that was one of the key aspects of this particular tool. What we also have to consider, is, well, sorry, let me take a step back. What we also want to consider with this river connectivity in terms of cumulative effects, I had mentioned that previously. If you were, say, looking at just even the simple one on the left, the network on the left with the barriers, if you wanted to reach, you know, from the river mouth to the area above E, you would have to pass barriers A and E. So if barrier A was completely impassable, well, you know, going and trying to fix barrier E is going to make absolutely no effect whatsoever unless you remove barrier A first or improve its passability. So that's what I'm talking about, an interactive effect. We have to consider how the barriers are kind of interacting together to produce overall longitudinal connectivity. And so that's one of the key aspects that the tool also considers. What it also considers is backwater effects. So here's kind of, you know, if I have this little simple one up above, what barriers do is the water kind of backs up as it goes behind the particular barrier, obviously. What you can have though is then when you go and try and modify these particular barriers, if you look at the lower figure there, I'm kind of lowering barrier 2. What that's going to do is then reduce the head at barrier 3. So if there were a hydropower station there, that would actually be very good for hydropower because it would increase the hydropower there. It would also increase the passability at barrier 2 because you're potentially lowering the head difference there. So maybe potentially improving passability there. So you could consider that as a kind of a double win, if you will. But we also have to, you know, things get much more complicated. If I remove barrier 2, well, again, there's still possibly interactive effects with barrier 1 further downstream from barrier 3, still raising the water level at there. And it continues as well. So again, we have to consider all these different combinations. Remove barrier 2 and lower barrier 1. So it basically produces these large interactive effects on conic passability for fish. So we also had to consider shipping. Now, this is a very simplified way of how we got a fleet of different possible ships you might have, the tonnage that they can handle, the maximum water depth they can go through, how much it costs to ship per kilometer, and various other things. But what you can effectively end up doing is kind of come up with these kind of cost curves of minimum water depth through the navigable portion, and then trying to see how that will affect annual shipping costs. So here's a particular example from our case study, which I'll talk about, the Neckar River in Germany. Those are two cost curves for annual shipping and how they would be affected by adjusting the minimum water depth through the main water course of the Neckar. Again, the tool needs to consider lots of different things in terms of how the cost for installing hydropower will vary, and it's not a very simple linear relationship, basically. So if you install lots of hydropower, it doesn't cost a lot, per unit is less expensive than if you install a small amount of hydropower. And it also varies quite a bit if you're installing new hydropower versus trying to retrofit. So again, these are kind of things all considered within the tool. So really, what is an optimization model? It's really effectively a mathematical model. So I guess I'm sure this is completely really clear to everybody, but it's really just to illustrate that there is a lot of kind of sound mathematics going behind it. And really what we're trying to do is maximize some kind of combined combination of our key performance indicators. Each key performance indicator is possibly some very complex function of the different barrier mitigation and removal, which is X, and what I install for hydropower expansion. I might have some minimum requirements for my KPIs. I can only have certain combinations of projects being implemented in combination with each other. And basically I need to decide, do my barriers removals, or do I how much hydropower to expand? Just to kind of jump out here. So that's a very simplified version of what's really going on here. These are all actually the whole set of decision variables that you have going into this thing, and lots of mathematical equations. So it'll make you kind of make your head spin if you want. So basically lots of sound mathematics going behind the scenes there.
Do you still need a lot of time, Jesse?
No, I'll be able to wrap up maybe in about, can I get 2 minutes maybe?
Yeah, okay, 2 minutes.
Okay, so here's my study area in the Neckar River. It's got loads and loads of barriers all over the place. And so what we did is compiled a large database of all the different weirs, dams, culverts, shipping locks. We had to get all the hydropower information, all the flow estimates, all the natural water depths, shipping cost information, etc. That took lots and lots of time. We had to figure out what are our available options for mitigating these particular barriers. So you got do nothing, install passes, lower or raise barriers on the main Neckar, possibly remove barriers as well, or replace culverts if you're off the main Neckar. We investigated in depth some particular planning scenarios. This is kind of a list of all of them, but I'm not going to go into much detail. I'll mention just highlight a few of them. The current situation, so current connectivity, surprise, surprise, in the Neckar is very, very low. The main, the best well-connected sections of the river are on the main Neckar River because it has lots of fish passes. And then here we're going to kind of go and put the tool into action and say, well, what happens if we want to go and maximize connectivity? Well, lo and behold, you can actually get like a whole 700% increase in connectivity. And if you can see from the figure, all the green riverbeds, that's highly connected river. So we can increase it a lot, but it comes at a very, very high cost. It's partly to offset lower shipping, and hydropower potential and revenue both reduced. So there's trade-offs basically, and you have to consider these. You could try and also, you could say, look, all I care about is maximizing hydropower, in which case you could actually increase hydropower by almost close to 15%, with actually little or no impact on connectivity, but admittedly still very low connectivity. Again, you could say, okay, all I care about is minimizing my cost, and here you can actually minimize your cost by raising some of the Neckar dam structures to increase the water depth, so more ships can transport stuff, and it will lower your overall cost. And again, it wouldn't have very much impact on hydropower or revenue. So
Again, I'll point out this particular scenario. So we considered, okay, well, what happens if you want to increase connectivity, say by 200% and increase hydropower by 10%? Again, this is one thing you could go after, and this is what the tool is really, I think, really designed for, is fine, you can get much better connectivity on the main Neckar, still kind of pretty low on the minor tributaries, but it'll go and increase hydropower by 10%, and yes, it will increase cost by 22%, so you know, no free lunch. But this might be particularly possibly an attractive scenario for planners. And so what the tool helps you do is sort out what are the best options for achieving these particular goals. And it'll kind of do it in the most cost-efficient way. So little summary, it's really here is, I think it really is a powerful tool for systematically planning out actions. It's some of the key aspects of it is that it's able to handle multi-threaded rivers, which occur in real life, and it really can balance multiple socioeconomic factors that are important. So, you know, it's not just connectivity, there is hydropower, there is shipping, there are, you know, water supply, there are other issues at play, and we need to balance these off. And I think kind of this little demonstration with the Neckar River kind of really does show that there are trade-offs among these different aspects, and, you know, gains in one will come at the expense of others. So, but what the tool does is help you sort that potential trade-offs out. So that's it for me. Thank you.
Okay, thank you very much. Thank you very much, Jesse. You showed the complexity and how the tools can help with getting through that complexity. Kinga, are you there to tell us more about the mapping of ecosystems services that has been done in AMBER?
Yes, hi everyone. I'm going to try to share my screen.
Almost, not yet. There it is.
Okay. Okay. Yes? Does it work?
Yes, loud and clear.
Okay. With ecosystem service mapping, we had to face some critical issues regarding barrier management. First is that there is always a number of actors which are involved in water-related issues, and very often those are people or users, including nature, beyond regular suspects. Then long existing barriers, of course, led to establishing a new city state. So you have completely different water regulation services and climate regulation, and also it affects, for example, agriculture. Impact of barrier may exceed the impact, the direct impact zone. So we started to think how to figure it out. And of course, there are different effects of barriers upstreams and downstreams. And this is, barrier management is a big spatial planning issue, in fact. So in AMBER, we wanted to look a little bit at natural capital and at ecosystem services. And we find out that for a project like that, which is very much focused on biodiversity and direct river services, we are in trouble. We can use models which are data intense, area specific, and very complex, and very often they involve other models. Or we need to use stakeholder opinions. This is time intense, this is skill based and trust dependent, and sometimes you simply don't have this stakeholders behind. We had also demos of different scales. In many cases, we did not have any historical background to trace changes. So what happened to ecosystem services when the barrier was built? Both capital and services go beyond riverbed. And we also promised in the project to anticipate climate change effects, which was very tricky. So in fact, we took a threefold way out of this trap, just sticking to land use data, which are commonly available data. And we decided to first have a look at stakeholder opinions, but just based on very small focus groups, and then switch to some modeling, which will be based on global data. And we have some extra, which is RESI approach. So for stakeholders' opinions, we decided to work with small focus groups, and we use the set of ecosystem services as listed in CISIS matrix. We ask our stakeholders, scientists, experts, anglers, decision makers, or other people available at sites, what they think, which kind of service they found as declining, and what they lost due to barriers. So on the left, I think here you have above them opinion, and here you have below them opinion for one of our demos, which is Wattle Horse. What you can find here is, for example, that people consider that they lost, of course, services which are related to smell mediation and erosion due to dam building. Those living downstream lost potential for energy production. Those living upstream gain climate regulation issues and services. And of course, a dam brought some possibilities to use surface water for non-drinking users. So we try to find out what stakeholders think, and then we switch to model. In fact, two models developed by King's College London and AMBER Tech, and this was collaboration with another project, NIAT, the Costing Nature and Water World. Costing Nature is an online tool based on global data, which allows you to map 13 ecosystem services and as potential and realized. So in fact, you map services and stock, this model is not showing you individual services, but rather aggregations, the bundles of services and relative contribution of each service to importance of the place, let's say. And Water World is a model which is based on hydrological modelings and climate scenarios, and it enables you to choose one of dozens scenarios which you want to choose. We have chosen A2 scenarios of business as usual, and it allows you to model, for example, precipitation or temperature according to the scenario of your area. Why we have chosen this type of tools? They are online. You can just log there and for free, and you can use them freely. The maps are there. They use over 100 information sources on different issues, climatic and land uses and urbanization densities and so on. And you can also upload your zone of interest, and you can also add economic evaluation if you know the prices of particular services, which we didn't do because we didn't know them for demos. Just a few words about advantages, as I said, especially explicit rapid analysis based on global data, ability to make projections, use of hydrosheds, which is concordant with AMBER approach, and you can very fast identify either climatic or services hotspots. But the models operate in large scales. That's how we lost some of our demos from analysis, because it was not possible for small demos. It's coarse resolution, of course. There is no mapping of individual services, and it does not focus on water-based services. However, it focused on services which are available in watersheds. And it's partially documented. You need quite a lot of data if you want to make it very precise. Anyhow, what type of ecosystem services we mapped? It's timber, fuel wood, grazing, water provisioning, fish catch, carbon sequestration, natural hazard mitigation, nature-based tourism services, environmental aesthetic quality, wildlife services, and these services. And costing nature shows you those services in units between 0 and 1, so they and it aggregates it into bundled ecosystem services. And just to show you very briefly how it operates, it creates you a map, and upper maps are for Włocławek River, Włocławek Reservoir on Vistula River, which is in Poland. It's a huge demo site. That's why you can see that the roughness is higher. And below you have Guadalhorce, Guadalteba, and Conde de Guadalhorce system, which is smaller. So you can see on your left, or my left at least, you have natural capital in both cases. And on the right, you have ecosystem services. So how much out of natural capital is in fact used by people. So what you can see is, for example, that ecosystem services in terms of Polish side are very much aggregated around cities, of course, while natural capital is aggregated out of very intense use land use zones. What is also interesting here is that for Spanish case, for example, you can see how much of services are used downstream of reservoirs. It's very intense, and this kind of use is related to reservoirs, even if it's not directly around reservoirs themselves or within direct reservoir impact zone. And I just wanted you to show how you can indicate in literally each point of this catchment what is the contribution of particular service to the importance of the place. So here, just for this one side, you have natural capital and ecosystem services. And what you can see from here, for example, is that in terms of natural capital, so potential, which is brought by the area, in this case, within the reservoir impact zone, is, for example, hazard mitigation, because we have still wetlands there. It's timber value or fuel value, non-wood forest value. So those services like hazard mitigation is here, for example. Those are those services which we don't use much. Those which we use are artificial fisheries allocations, carbon sequestration, grazing services, aesthetic value, and nature-based tourism. So these are completely two different pictures. And this is interesting because it means that, for example, hazard mitigation, which is a potential service, is not used here, while we decided to create reservoir to provide hazard mitigation. So it gives us this knowledge that sometimes maybe it's better to have a look at natural capital and nature-based solutions instead of introducing completely different gray solutions to the place. And it's just the lower part.
Sorry,
shows
can I
yes?
just question, do you need, how much time do you need still?
3 minutes, 3 minutes maybe.
Can you try 2 minutes?
Yes, I will.
Okay, thank you. Okay.
Okay, it's just to show you that this is costing nature picture, and this is water world picture. You have precipitations here for spring, summer, and autumn, and temperatures here. And what you can see is that the strongest decrease of value happens when it's blue. So in fact, our reservoir in Poland is in the zone which will not experience too much drought, maybe, but it will experience increase of temperatures, what may also influence the water balance. So these are just conclusions from the whole study on 3 cases, which is that we need to reevaluate the stream flow changes because the occurrence of high and low flow will probably increase. So we need really in landscape planning consider presence of reservoirs, of course, but maybe also presence of other systems very often dependent on water, which can protect us against flooding and other hazards. And those areas must be really excluded from any development because they protect us from both flood and drought. We need to think about ecological design, but considering functionalities of different areas, because not necessarily working only on the banks of river and reservoir will help us to achieve a good solution, good results. And we need to think about expansions of retention potential using natural capital, which is at our sites. I think that something which we really must focus on is that adaptive management of existing barriers may be difficult because many of them were not created considering climate change, and this climate change will influence very strongly land uses. And just to say 2 words about another approach, which is under process. So I will not show you any results, but because we lost a lot of small cases from this big scale modeling, we switched to River Ecosystem Service Index, just trying to develop it based on to simplify the approach. We are in contact with RESI team. Because this kind of index allows you to deal with small demos. Just you divide them into small sections and you try to assess all these ecosystem services for each of the section. The original approach is very data intense. That's why we want to simplify this to kind of observation, something which you can use with more available data, like global data maybe. So we hope to have at least some of those services already assessed for few demos for Fish Passage 2020, which will hopefully happen in Lisbon this year.
Yeah, I hope we can do that live and not via webinar, although it's working quite well, I have to say, so far. But we hope to see everybody at the end of June at our final event of AMBER in Lisbon, right before the Fish Passage conference. Kinga, thank you very much. Ecosystem service, very interesting. You're stressing the climate change as something major we have to look into. I think we all agree to that. Meanwhile, I think at Swansea, you have been looking at all the questions that have been, or the answers that people have been put in on the questionnaire that we sent out in advance.
Yes.
Carlos, yeah.
Yes, that is correct. We have just summarized the data, and perhaps I can.
Maybe you can share the screen, or do you have to do it by?
Yeah, no, we have a screen. Can you see that?
Yeah, it's coming. Yeah, there it is.
Okay, so this is what Mathilde and Richard have done. So
done that really quickly.
The 27% of the participants answered the 3 questions that we put to them, and we are hoping that the rest of participants will provide their points of view, because this is extremely important. So we asked 3 questions. The first question was, what are the main practical challenges for quantifying river connectivity? And Richard has done a wordle here where you see that perhaps the most important or common word is lack. So is lack of something, a lack of barrier data, a lack of knowledge on the effects of connectivity. If we put these answers into a coherent framework, we see that most people pointed out that it is lack of availability of information is one of the main issues. The characterization of obstacles is the second issue, and perhaps locating the barriers where the barriers are present is perhaps the 3 or the 4 main challenges for quantifying river connectivity, with also, which is similar, how comprehensive the existing databases are. Okay, so this is what the people from the Ecostat work group have told us, and as I said, this is based on 27% of their respondents. The second question was, what are the main practical challenges for assessing the impacts of fragmentation? And again, we see the word lack being highlighted, and putting this into context, we see that it is the absence of cost-effective tools, is the fact that impacts are often perceived to be site-specific, which obviously makes generalization difficult. It has also been pointed out that there is lack of data, and finally, that there is perhaps lack of tools to enable us to prioritize. So these are the practical challenges for assessing the impacts of fragmentation, the main ones. And finally, the third question we put to the group was, what are the main practical challenges for restoring connectivity? And what the group said is that number one is lack of a specific budget, or presumably a sufficiently high budget. Second, which I think is very interesting, is lack of involvement of relevant stakeholders. That's very, very important. We cannot restore rivers, we cannot restore connectivity if people don't care about it. And the third one is, again, prioritization, lack of tools to enable us to restore connectivity in the most cost-efficient way. So these are the three questions we put to you, and this is what the group has told us. And we will, of course, summarize the data and add this to the report.
Okay, that's very interesting. So this is what people are asking for if we want to improve the situation in European rivers. And obviously a question that we ask all of the people who have attended this, like, so does AMBER, does what we present so far help with that? We have asked 4 people from different sectors how they look at that, to give a first reaction. One from the NGO perspective, one person from the water authority perspective from Sweden, one person from the water power sector, electricity sector, and one from the environmental agency. But first, maybe Sergej, you are from the environmental European Environmental Bureau, NGO working in Brussels. You are for a long time already involved in this issue. If you've listened to this morning to the different presentation, what is your first reactions? Are you there, Sergej?
Yeah, good afternoon. I hope you can hear me. And thank you very much for pulling this together, because I thought that was a great use of time to quickly understand different tools that AMBER project.
Can you talk a little bit louder, Sergej? I don't hear you very well.
I can try to move closer to the mic. Is that better?
That's definitely better. Thank you.
Very good. Thanks, Ariel. Yeah, so I think it was a very, very useful presentation of different tools. And I'm just to express my personal opinion, because we obviously didn't have time to consult with colleagues on this, etc. So we'll be looking forward to read the presentations afterwards and watch the recording of the webinar as well, because there was a huge level of detail that I think we may have missed. And I think overall, just kind of as a general comment, I think these are very, very useful tools that also seem to be coming at the right time. So I think what would also be really, really important for their applicability, to make sure that they are either relevant for the implementation of the Water Framework Directive, for example, so they really need to take the logic of the directive on board, or to really serve a particular political purpose, like Jean informed us about the upcoming biodiversity strategy that would hopefully have a target on restoring river connectivity. So the idea of some of these tools can help us with prioritizing which barriers need to be removed as a priority would be extremely helpful. So I can definitely see the use of the tools, and but I think where I think we can definitely strengthen them, how they can be made more applicable in current political context.
Oh, sorry. Thank you very much, Sergej. So I hear that you are definitely interested into the results, and also, as I understand, would appreciate if we distribute a bit of the information also afterwards, because this is a lot of information at one time.
Yeah, that. But I understand that already will happen. So if we can, if you can share the recording and the PowerPoints, and then if we have questions, we can go to specific people.
Yeah.
Because I'd love to talk to Jess, for example, on the optimization tool, because I think there are some things in there that don't take into account the Water Framework Directive elements. For example, cost recovery from some of these sectors. But that is definitely something for a different follow-up discussion. Thanks.
I think Jesse was very open to discuss that indeed. Maybe with regards to the, I wanted to talk about the presentation, but we can do that afterwards. Maybe we go to Katarina. You're from the Swedish Agency for Management of Water, of the Water Authority, so to say. Yeah, can you have what is your reaction to what you've heard so far this morning?
Hello, everybody. Can you hear me properly?
Yes, we can hear you. Maybe you can also share your screen, so it's a little bit easier to see who is talking.
Your video.
Yeah, I'm sitting at home, so I think my connection is not very good. So,
okay.
Due to kind of a corona effect that I'm sitting at home.
All right. Yeah.
Yes. Thank you for having this workshop as a webinar, since we had to cancel the physical Ecostat meeting in Paris. So I appreciate that you did this and on such short notice. And I think it was very good, even though you didn't have much time. So thank you very much. I just want to start by saying that. And then your question was my comments regarding your presentations and the work that the AMBER project has presented. And I think it's very important job that you have made. And as a lot of people answered in the questionnaire, there are some difficulties when it comes to estimate the impact from barriers. And this is the experience that I have from Sweden as well. And it's not just identifying the impact, but also finding the different barriers that is sometimes difficult. So it's good to have a lot of tools developed. Thank you very much for doing this. Sometimes I think, though, that different tools can also be difficult to learn how to use and learn how to understand the result from the different tools. So I think that's very important to bear in mind once you teach the tools, that people really need to have time to learn the tools if they're going to be effective.
Yeah, thanks for that. I mean, that brings back to the some remarks that we saw when Jesse presented. Somebody asked, "Is it easy to use?" And now I also hear from Sergey asking, how does it take the cost into account? Maybe Jesse, this is something that you can react on that, Jesse.
Sorry, yeah, I don't have the I can't see the message with the cost question. I'm sorry, I'm looking in chat. I don't see it specifically.
Sergey, can you no? It's Sergey was saying it. Sergey, can you repeat your question for Jesse?
Sure. No, it was just an example of some of the things that I think would be really useful that these tools build strongly on the Water Framework Directive. So the optimization tool was just an example. I think again, and I may have totally misunderstood it. That's why I would like to clarify it with Jesse afterwards. I didn't see how the cost recovery from some of these economic activities are being recovered in order to enable some of these measures to put in place, which is a legal requirement under the WFD. So, so that was kind of a point that I was trying to make, that it would be important that these tools really follow the logic of the legal requirement of the Water Framework Directive for them to be used widely by river basin authorities, etc., etc. And that was really just one element I wanted to highlight, that I'm not clear how the current tool takes that on board. Thanks.
Yeah, sorry. Yeah, I understand what you're saying. Yeah, so the simple answer is no. The tool was not specifically designed for Water Framework Directive specifically. That said, it can be, I think, quite easily adapted to incorporate aspects of cost sharing or whatever it needs to be. So it is currently more at a demonstration purpose or demonstration level, the tool, but it can be certainly improved, modified, adapted further.
Okay, and regarding what Katerina was saying, that we need to make sure that people have the time to dive into the tools, we have to make sure that the tools are being used properly. How do you look at that, Jesse? If it's
well, I think it's on a case-by-case basis, in the sense, if you were, for Piotr's model or Simone's model or my model, obviously you would need, I think, maybe a little bit of maybe some presentations with people. I guess it's possible to come up with short little user manuals and that sort of stuff if these tools can be generally shared. But I think it's a little bit hard to say, because I'm not sure what tools can be publicly shared, or if there's a confidentiality issues with different parts of it, etc. So I guess that one's a little bit harder to clarify. I have, for my own part, I have done lots of kind of tutorial type things, like at the Fish Passage conference, where we have 50 people come in and we explain how to use these types of tools that we have. And so that's one vehicle for giving more information about details of these types of things. The art, which I did kind of try to mention, is that tool I have is very high detailed, high granularity in terms of the data requirements. There are kind of more course level models for prioritization that you can use at at broader spatial scales with less data requirements and that are easier to use. So I've had a lot of experience in developing those types of tools. And I'm generally happy to share those with people.
Okay, thank you. I think this is something we need to also take home when we write a policy briefing, is also about how to make sure that people are guided into what tools to use and how.
Arian, may I interrupt there? Just to say two things. All the tools will be publicly available in our website, and all the tools will conform to the same format. And I don't know if you can say it, but this is what we have in mind. And we are in the process of compiling this information for all the tools. So all the tools are going to be presented to the user in a way that the user will know who is the author or developer. There is a brief description of the tool. There are links to where the tool can be downloaded or used. There is a description of the problems or needs addressed by the tool, improvements over state of the art. How is this tool an improvement over previous approaches? Training needs, examples of use. Some of our tools, people have made videos in YouTube. And finally, we have a section for references and also any updates. So all the tools will conform to this format, and all of them will be publicly available in our website. But as Jesse says, we're still working on making sure that they are harmonized properly.
Excellent. Thank you very much, Carlos.
Can I please add something, Katarina here?
Who is that? Katerina, yes?
Yes. I just wanted to say that I agree with Sergei's comment that it is important for the management and the different authorities and competent authorities in implementing the Water Framework Directive, that these project and methods in some way, even though if it's not specifically part of the Water Framework Directive, it is important to make it easier to somehow explain how it could or should be used in connection to the Water Framework Directive, because it makes it much easier for the different stakeholders, not only the competent authorities.
Okay, thank you. This is a takeaway home message. How do you call it? Anyway, thank you.
Yes.
Okay, then next, Martin Schletter from Eurelectric, working in the water power industry. Can I ask you, what is your reaction?
Hello, greetings from Austria. So first of all, I'm not from Eurelectric, but in Ecostat, I'm representing the European Water Association. But I can give a short statement from the hydropower point of view. So I think the projects like AMBER as well as Feed Hydro, of course, contribute to sustainable river management because we need knowledge, we need to understand our systems in order to develop sustainable measures. What is also important to keep in mind is that most of our European rivers are multi-stressed rivers, and therefore it's often not a single factor, but it's a combination of different factors we have to keep in mind, and that will in the end determine the success of certain measures. If we are thinking about connectivity, on the one hand, we are mainly talking about longitudinal connectivity, which is, of course, a first step. But here we also should keep in mind the 4D concept of river ecosystem, thinking about longitudinal, lateral, vertical, as well as temporal connectivity. And for the hydropower sector, I think we can see one clear thing. On the example of Austria, we can say that there are about 30,000 barriers, more than 30,000 barriers in the river network bigger than 10 square kilometers, and about 10% of the barriers are related to hydropower. So what we've seen from the first river basin management plan is that the hydropower sector really invested into the re-establishment of connectivity. In Austria, that's something like 140 measures with an investment of more than 200 million euro. So I think hydropower also is a good partner on the way of setting measures and also developing suitable measures. On the other hand, what I missed today in the discussion is a differentiation which is very important, because of course we need the European perspective, but Europe is very diverse. So there are a couple of countries where it's very important to talk about eel and Atlantic salmon, those diadromous fish. But in many other countries, those diadromous species are not an issue. So we have to differentiate and also think about different combinations of measures in order to reach the targets of WFD in the end.
Yeah, thanks for that. Maybe Carlos, you can react on these two issues that being put forward by Martin. That longitudinal connectivity is only one aspect, and the other is how do we take into account the different aspects that countries, the differences between the countries. Carlos, can you?
Yes, I couldn't agree more. Absolutely, one size is not going to fit all, and eels and salmon are not going to be relevant to large parts of Europe. But that is why we need to stress that the task here is to focus on continuity taking into account the whole ecosystem. So it's not just fish, it's not just salmon, it's not just eels, it's sediments, and appreciate that there are big regional differences. So that's why our tools need to be also flexible enough to be modified and applied in different contexts. So I couldn't agree more with Martin.
Okay. Okay, and also thank you, Martin, for making clear that, of course, the hydropower sector is also, can be of help improving the situation, as you explained. I think that's really good to acknowledge that part. Definitely.
Thanks.
Thank you. Then Peter Christensen from the EEA. Maybe you have also listened to this story and you've been involved in this issue. Maybe you can say something too. European Environmental Agency. Are you there?
Yes. Can you hear me?
Yep.
Okay, that's fine. I'm speaking from my phone, so I will not put on my video. But first, I want to thank for an interesting and informative webinar. I think I've learned a lot already during these 2 hours. I think also the AMBER project has done a good work on several issues. First, I think that the Atlas and will be a reference for having an overview of barriers in European rivers, and can be also used in connection, for example, with a target on making barriers passable or free flowing rivers, which probably will come in the coming years, and also could be a target on river basin management plans, river basin districts, country level, on making many of these barriers passable. I also think that the tools developed is an important part of the management, the mitigation, and fits very much into the river basin management plans, that the work on those. What I partly missed from today's presentation is the linkage to the Water Framework Directive and to the river basin management plans. Because actually I think many of the river basin districts has already a fair overview of their barriers. Of course, there's different approaches and also different approaches to implementing measures. We just heard, for example, from Austria or from the hydropower sector that there were 30,000 barriers in Austria. And actually, I think the management plans maybe only has the focus on 1,000 or 2,000 of those. So it will take very long time also to make many of the barriers passable and to implement measures. So I see very much the AMBER projects or its tools in this process. For the moment, river basin districts are preparing their draft river basin management plans for the third cycle. And I think it's very much important to think about them as management plans, that when you have identified, one example, 1,000 barriers in your river basin district, then it's important that you have see them as a management plan. Then you have to make some of them passable, at least during the next cycle. And also to illustrate what could be the measures for the next cycle. And this is my hope that with the draft river basin management plans coming here within the next year, there can be a lot of discussion on how to make many of these barriers passable, or are the river basin management plans ambitious enough on making the barriers passable. It was my comments on.
Yeah, thank you very much. So what I get from this is that you see the value of what has been presented, the more information, more information about locations of barriers, etc. But now it's time to get it more into the river basin management plans, and for that we need not only information but also prioritization. There the tools have been presented, but I hear sort of a looking forward to how to do that. Is there somebody who wants to react on that? How we can progress on this? What can we do to support that more? To integrate what has been presented by AMBER into practice of people working on the river basin management plans?
If I would possibly chime in, if it's possible.
Yeah.
Oh, my connection is unstable, so I will stay anonymous.
Okay.
I think that the first to adapt the tools to fulfill the specific format and provide results in a format that is needed for the regulation. It's relatively simple cosmetic approach. But I also believe that it goes both ways, that also people who are working on the river basin management plans and work as well as working on the regulation development and the legal development need to be aware about the possibilities that the toolkits are providing. So it's not going only one way, and I think that providing this information further and thinking in creative way how this could be adapted for the purpose that is needed in the river basic management plan, that's one also of the important topics.
Yeah, thanks. So you're saying, and you have the researchers coming from one side and policymakers from one side, and we need to make sure that the data is properly, or the information properly exchanged and used. And we might have to do that more on a national level, even maybe. But I'm not sure if that can. Well, the question is how to take it forward. Some other reactions from people about that. Wouter, maybe you want to say something about it from Ecostat's perspective. Wouter, are you still there? No.
Be on mute.
He's on mute. You're on mute, Wouter. Let's look for Wouter for a moment.
Yes. Oh, here he is.
Here he is. He's not.
Oh, it says.
Oh, he's very bad connection. Oh, that's a shame.
Yeah.
Okay. Carlos?
Can I intervene?
Yeah, Martina. Of course.
Yes.
Yes, from the water perspective. Yes.
Yeah, I think there are some basic actions that could be taken for supporting the directive, starting from the basic information that are needed when we detect barriers and we want to have an inventory. Instead of, we already said this several times, instead of doing classification based on the objective, I mean, barrier passable for a certain fish, barrier passable for another target and so on, just detect the barrier in all its objective characteristics as a structure, as you are doing in AMBER, and then you can use that data for everything, for any aquatic organism, for sediment, for whatever, and then you have an homogeneous approach to an homogeneous standard to report this barrier, and this is quite useful. It's comparable across Europe. You can use it several times. So once you have an information, that information is, you have the basic and it's standardized. So I think that's already a step forward. And my suggestion was that because this information is crucial for characterization and assessment of water bodies, that you have any way to have it, then why not collecting it in this standardized way? It doesn't cost that much. It needs a bit more of involvement of member states, maybe, to adapt their way, or maybe apps. You developed an app as well when you go on the field, didn't you? Yeah.
Yeah. Wouter is not able to say something because of bad connection, but he's right, all of us, that the aim of the webinar was to inform about the tools, right? So
yes,
the application by member states has to be addressed more maybe in the Ecostat group, and there's a workshop foreseen. I think that's exactly what is needed to take
exactly.
So
the issue is that we thought that this kind of discussion could be carried out inside the Ecostat, but then the Ecostat meeting could not go on.
No, I think that's a perfect conclusion for now. So that's clearly request from both sides to continue on this, and we need time, I guess, to make proper use of that as a next step. So I think we unless there's somebody, Carlos, wants to say something to finish up the webinar for now, Carlos.
Yes. So we made some notes which will serve hopefully as a closing remarks. And basically, I think that it's very clear why connectivity is important. It has been pointed out, freshwater ecosystems are the most valuable in the world, but also some of the most threatened, and they are subjected to multiple stressors. So connectivity is one of them, barriers is one of them, but there are also other stressors that often act in synergy. I think that, Jan pointed out that there are some instruments out there to restore connectivity. We have planning instruments, financial instruments, there are legal instruments. There is also a legal framework, which is mostly about the Water Framework Directive. There have been some very encouraging improvements in connectivity. Some migratory fish are reaching the headwaters of watersheds in Europe in ways that people have not seen for the last 200 years in some cases. But of course, rivers are just more than fish. I think it's very encouraging also to see that now the next step, the next phase, which is how do we apply these tools, is something that Ecostat is going to take on board, and that will hopefully be addressed in forthcoming workshops. I think Martina also summarized very well why all these problems are a matter of scale and measures. And I think it's important to remember that it is deviations from baseline, from reference conditions that we are trying to address here. I think that our speakers, they provided a good overview of the range of tools that will serve to address different problems. And obviously, these need to be provided in a coherent, harmonized way so that they can be used. I particularly liked, I think that it is also with new computing capabilities, Simone and his team, they have done, taken this Pareto approach to actually look at all the potential combinations to try to come to optimal solutions in terms of dam location. And the same approach could be used for planning new dams in Europe and also for identifying those that cause most damage, which are obsolete. The same approach was taken by Jesse in many ways, and he stressed the fact that here we are also looking not only at multiple stressors, but they are necessarily multiple trade-offs. And I think that trade-offs is the big thing that also Kinga expressed. I particularly like what she stressed, that at the end of the day, it is people's opinions that matter. And I think it's useful to remember about temperature. It's very often that people feel temperatures in different ways. And it doesn't matter if you tell them that the temperature is 30 degrees. If they feel cold, they feel cold. And I think it's important that we take on board people's opinions, because without them, restoration of connectivity will not be achieved. And finally, I think our panel speakers, I think they have summarized very well some of the challenges for applying these tools and some of the complexities of such a heterogeneous continent as Europe. And I will finish by saying that I think that this is a very prime example of where we need to think globally, but act locally.
Yes, okay, thank you very much, Carlos. That I think summarizes for now the webinar perfectly. Wouter just asked me to close the workshop because his connection is so bad that he cannot do it himself on behalf I'm here as chairing for Ecostat. So I think we can finish our webinar for now. I hope that everybody has we will create a policy briefing, and the presentations will be made available through the website. But we have to look when. I think, but we'll come back to you. And I would like to take the opportunity just to show you a first version of our magazine that's going to be presented in the 15th of May. We are very proud of it. It's full of nice stories onto. This is full of interesting examples how to make use of AMBER results, and also on a, let's say, a not so difficult way. And now I see that somebody is asking to have a summarizing page of the conclusion of the meeting. I'm sure that will be looked at, and maybe Carlos or Victoria, you want to say something about when the conclusions of this webinar are made available?
Yeah, so we will be preparing some, let me turn the video on. There we go. We will be preparing some notes of the meeting today and circulating those hopefully very, very soon, along with the presentations that have been given today.
Okay, now, thank you very much.
No problem.
And, thanks everybody for being here, and well, hope to see you all at least also in Lisbon, if possible, of course, at the final event of AMBER and at the Fish Species Conference. Thank you very much. Bye.